Volumes using cross sections. In the previous video, we talked about finding the volumes of a solid using the slicing method. In this video, we're going to talk in particular about volumes of solids of revolutions. So for this, we're going to let f be a non-negative and continuous function on the interval AB, and we'll let R be the region bounded above by the graph y equals f of x and below by the x-axis, and also on the sides by the line x equals a and x equals b. We're going to take the graph of y equals f of x and revolve it around the x-axis to generate a solid having circular cross-sections. So I'm going to take this, I'm going to revolve it around, and we'll end up with a circle. Since the cross-section at a point x has radius f of x, because going from here to here, the height there is y equals f of x, we have that the area of the cross-section is equal to the area of a circle of radius y equals f of x. So we get that the area function is equal to pi times f of x squared. So the method of disks says this: let f be a non-negative and continuous function on the interval AB, and let R be the region bounded above by the graph y equals f of x and below by the x-axis, and on the sides by the lines x equals a and x equals b. Then the volume of the solid generated by revolving this region about the x-axis is the definite integral from a to b of our area function, which is the definite integral from a to b of pi times our function squared. So let's do an example. Let's find the volume of the solid obtained when the region under y equals the square root of x over the interval 0 to 4 is revolved about the x-axis. So the first thing you should do is sketch a region of what it is that's being revolved around the x-axis and draw the radius, or a slice, at x and indicate the direction of rotation. Right? So here's the graph of y equals the square root of x. Here's some slice at x, and we're going to take that and we're going to revolve it around the x-axis. When we do that, we're going to get a circle of radius square root of x. So we get that our volume is equal to, the formula says, the integral from a to b of pi times f of x squared. A is going to be where we start making our slices, and b is going to be where we end making our slices. So we're going to start here at 0, making our vertical slices like this until we get up to 4. So a is going to be 0, b is going to be equal 4, and then our radius is our f of x, which is the square root of x. So our volume is equal to the definite integral from 0 to 4 of pi times the square root of x squared dx. So now we can just go ahead and evaluate this integral. We squared the square root of x. We find the antiderivative of pi x. We evaluate it from 0 to 4 to get that our volume is equal to 8 pi. Alright, let's do another example. Let's derive the formula for the volume of a sphere of radius r. So now you have no excuse not to know what the volume of a sphere is. If you don't remember the formula, you know how to find it now. Let's see. The solution, think about it. If you think of a sphere, you take a semicircle and you revolve it around, right? So let's say our semicircle is the upper semicircle above the x-axis, centered at the origin. So here's what it looks like, and we know the formula for that. It's y equals our radius, the square root of our radius squared minus x squared. We're taking that shape, we're revolving around the x-axis, so here's what one of the slices would look like. So the formula for volume is the integral from a to b of pi, our function squared. So this time when we're making our slices, we're starting over here at negative r, and we're slicing all the way across like this until we get to r. So our limits of integration are going to be from minus r to r, and our function is just the square root of r squared minus x squared. So our volume equation becomes the integral from negative r to r of pi times the square root of r squared minus x squared squared. Now all we need to do is evaluate this integral. First we square the square root here, and I notice that this is symmetric around the y-axis, so instead of integrating from negative r to r, I use a property that says that integral is going to be equal to 2 times the integral from 0 to r. Now, going from here to the next step, I can pull a pi out because it's constant, and then the antiderivative of r squared, well, r is a constant here, so the antiderivative is r squared x, and the antiderivative of x squared is 1/3 x cubed. So I'm going to take this and evaluate it from r to 0. So just plugging in the appropriate values and doing the subtraction here, we find that the volume of a sphere of radius r is equal to 4/3 pi r cubed. All right, so now let's think about more general solids of revolution. So let's suppose that f and g are non-negative continuous functions such that g of x is less than or equal to f of x for all x between a and b. All right, and let's let R be the region enclosed between the graphs of these functions and the lines x equals a and the line x equals b. All right, so we're going to take this region and revolve it around the x-axis. When we do that, it generates a solid having washer-shaped cross-sections. Since the cross-section at x has inner radius of g of x and outer radius of f of x, we get that its total area is going to be equal to the area of the disk generated by f of x minus the area of the disk generated by g of x. So from here, all I'm going to do is factor out a pi, and notice my area is now equal to pi times, you take your function f of x and square it, and then you subtract off your function g of x squared. All right? So this gives us the method of washers, which says let f and g be non-negative and continuous with g of x less than or equal to f of x on an interval a to b, and let R be the region bounded above by the graph y equals f of x and below by the graph y equals g of x and on the sides by the lines x equals a and x equals b. Then the volume of the solid generated by revolving this region about the x-axis is equal to the volume of the area of your cross-sections integrated from a to b, which is equal to the integral from a to b of pi times your upper function f of x squared minus your lower function g of x squared. So let's do an example. Let's find the volume of the solid generated when the region between the graphs of f of x equals 1/2 plus x squared and g of x equals x over the interval 0 to 2 is revolved around the x-axis. So the very first thing you should always do is graph the region. That'll help you decide what is your upper function and what is your lower function. So f of x is just a parabola with vertex at 0, 1/2, and it opens upwards, so it looks like this. And g of x is the line of slope 1 passing through the origin. So this is what the graphs look like. So when you do this, you can clearly see that f of x is your upper graph and g of x is your lower graph. And now if we think about, okay, I'm going to take this shape, I'm going to spin it around the x-axis. That means to figure out my areas, I'm going to cut a slice like this. And what I'm spinning around is this little part right here. All right? So my volume is equal to this formula. We said that I'm going from here to here, so I'm taking my slices at x equals 0. I'm going all the way up to x equals 2. So those are my limits of integration. And then pi, and now I take the function on top and square it. So that's the 1/2 plus x squared. And then I subtract the function on bottom squared. So that's x squared. And it's really important here that you do the square of the first function minus the square of the second function. It's not the same as taking the difference of the two functions and then squaring it. So be really careful about making sure you put the squares in the right place. So now we just go ahead and evaluate this integral. I expand out the squares here and here. I get rid of, or I combine like terms, which gets rid of the x squared term. This is easy to integrate. And once you do that, pause the video here and make sure you can do the algebra to get you to the answer of 69 pi over 10. Alright, so now, besides revolving around the x-axis, we can go ahead and revolve around the y-axis. There's no problem with doing that. The difference is now everything's going to be in terms of y. You talk about, I'm integrating from c to d, that's where you're making your slices going in the y direction for your disk method. And there's a corresponding one for the washer method. So let's see how we would use that. In this example, let's find the volume of the solid generated when the region enclosed by y equals the square root of x, y equals 2, and x equals 0 is revolved around the y-axis. So first thing we're going to do is sketch the region. And this time we're revolving around the y-axis, so let's put an arrow to make sure we know which way we're revolving it. Since we're revolving around the y-axis and I want to end up with circles to sum up my areas, I'm cutting my slices this way so that when I spin it around I end up with a circle. Alright? So now, since we're doing revolving around the y-axis, we're going to integrate with respect to y. That means we need to rewrite the equations as functions of y. So to do that, y equals the square root of x becomes x equals y squared. Alright, so our volume is going to be equal to the integral of where we're taking our slices from, c to d. So we're starting here at 0 and we're taking slices up to y equals 2. And then it's pi times our function in terms of y squared, which is y squared squared. Now we just simplify the integrand here. We find the antiderivative and we evaluate it from 0 to 2. So take a moment now to make sure you can stop and do the algebra to get you to 32 pi over 5. Alright, so sometimes it gets a little confusing when you're doing the disk and the washer about what are my limits of integration, what am I revolving around, what variable am I talking about. Here's just a few basic ones to help you out. When you start, always make a sketch of the graphs. And notice I here wrote noting any x-intercepts and intersections. So besides x-intercepts, you might want to know what your y-intercepts are. And when I say intersections here, I mean between all the different curves that are involved in the problem. If you're going to revolve around the x-axis and you're using the disk or washer method, then your slices are perpendicular to the x-axis because those become your radius. And then you're going to integrate with respect to x. If you're revolving around the y-axis, think about it, your slices are perpendicular to the y-axis. Those become your radius. And now you need to integrate with respect to y.